Today then is the equation of the line If I've got some data, if I've done an experiment and got some data and put the points on a graph, for example, a piece of graph plotting software like Autograph that you'll become familiar with as we go through the course, I can put some data points on the graph and I can use the Autograph to sort of zoom in on the data to see where the points are. But what I'm interested in is drawing some sort of function that describes the points. If I were to put a function into Autograph, then that would mean it would draw a curve or a straight line for me. And what I want to do is try and find a curve or a straight line that fits these points. And generally, the easiest one to draw is a straight line. So we can see these points suggest a straight line. So what I want to do is try and draw a line through these points, which will then be a function that we can use to describe this data. And so we're ending up with a formula that we can then use to describe what's going on inside this function, maybe to use it to find a value. I'm going to use the software to do it in a minute, but what we have here is a set of data, these data points, and I'm plotting up here, say on the y-axis. For this particular question, I think this was taken out of the textbook. This would be the volume in cubic meters of a gas. And along here, we're plotting temperature in degrees centigrade. And we find that as the temperature of the gas increases, the volume increases, it expands. And it looks like it's a linear relationship. Why does it look like a linear relationship? What do I mean by a linear relationship?
It's a set ratio. As one increases, the other one increases at a fixed amount.
Yes, a set ratio, that's right. So as one increases, the other increases at the same sort of rate, exactly right. And that's what these results are suggesting. So a linear relationship means that if I plotted the function or I plot the data, I'm going to get a straight line, which is what we seem to be getting here. Okay? So if I do an experiment and plot one variable against another, I'm looking for the relationship. What is the relationship between these two? If the data points are all over the place, one here, one here, one here, you know, all over the place, then I would conclude there's no relationship between this variable on the y-axis and the variable on the x-axis. If there is a relationship, I can try and find out what that relationship is. The easiest one, as I've said, is to try and find a straight line relationship between the two. If, however, these data points, as we'll see, don't fall on a straight line, there are ways around it. We can do something with the data to try to get it to look like a straight line, and then we can do what we aim to do today. So the technique we're going to use to find the equation of this straight line actually can be used with data other than data that falls on a straight line like this. So it's a more general method. Just a word on the variables. On the x-axis here, where we put the temperature, this is generally what's known as the independent variable along here. So we tend to put the independent variable along the x-axis. So that's the variable we're controlling. And when I looked at this problem in the data book, the first temperature is at 60 degrees C. We can see here that first data point is falling at 60 degrees C. The next data point is falling at 65 degrees C, 70, 75, 80, and 85 degrees centigrade. So in other words, we're controlling this variable. This is the independent variable, the one we're controlling. So the independent variable is often called a controlling variable. And then what we plot then is the dependent variable on the y-axis, which in this case is the volume. So this is the dependent variable because it depends on the independent variable. So in any experiment, if you like, or in an engineering scenario when we're looking at the relationship between two variables, we're always interested in two variables, one we're controlling called the independent variable and one we're observing called the dependent variable. There may well be other variables that affect this situation, like the pressure of the gas and other variables. What do we do with all those other variables? Apart from the independent variable that we're controlling and the dependent variable we're observing, what happens to all the other things that might affect this situation, this experiment? Yeah. They're kept constant, exactly right. Okay. We want to know how the temperature is affecting the volume. So the temperature will also affect the pressure. And so we want to make sure the pressure, which is the big variable we've got to then think about, is constant. So constant pressure while we're doing this. So all other variables that might affect it, we keep constant. And you will be doing, I guess, at some point, you know, and think about when you're doing it, what you're actually doing, because often you're told, right, do this experiment, but think about what you're actually doing. You'll find you're controlling one thing, observing something else, and keeping everything else constant if you're going to come up with a reasonable relationship between the two. Okay, so let's put this in our notes. So there we have this situation. Independent variable on the x-axis, dependent variable on the y-axis, and we plot the points. Now what I want to try and do is to come up with a function that describes these two. So let's go back to our autograph again, and what I'm going to do is type in, and we'll talk more about this a bit later, a function. Right, so I put a straight line on there, and the function that I've typed in here is y equals mx plus c. You can see it down here on the board. Here's a nice little tool. This function here. Okay. Oh, it didn't do it. Why did it not do it? Supposed to describe that. Try again. No. Okay. Maybe it's not synchronized probably, but anyway, can you see down there y equals mx plus c? That's the function I've just put in. What I can do is I can change the values of m and c. So let's have a look. I change m, that seems to be affecting the slope of the graph. If I change c, that seems to be affecting where the line cuts the y-axis, where the line cuts the y-axis around here, okay? The y-intercept. No, it's still not doing it. I don't know why it's doing that. It was working perfectly yesterday. So anyway, abandon that. So I change C and I change M. I can change the position of the line. So the job is to play around with M and C until we get this straight line to go through the points. So I would suggest if we're going to do that, the first thing to do is try and get the line parallel with those points by changing the value of M. Oops. I can change the step size so it's not changing at such a large rate, 0.01. That looks reasonably parallel now, would you say? And then I change the value of C, where it cuts the y-axis. Let's change the step size a bit bigger. Here we go. Come on. You can get it. here it comes. Like playing a computer game. Oh no, it's not quite parallel, is it? Now we get close. So I can change the value of m again. Change the step size smaller. And then go back to C again and change it. Okay. Until it sort of matches the points. I could probably fine-tune that. I could zoom in on those points and fine-tune it, use the software to come up with those values. And now what this is telling me is what C is, and C, remember, is the position at which it cuts the y-axis, and M is the gradient. So it looks like the gradient is about 0.16 and the y-intercept is about 15.34. So I've got this general equation, y equals mx plus c, which describes this linear relationship. I know it's linear, so therefore that means that x is only single power of x. It's linear. It's not x squared, it's not x cubed, it's not the square root of x, it's not any other function to do with x. It's just y is effectively directly proportional to x, which is what Richard was saying at the start. If we look at this data, what does it mean if it's a straight line? It means that if 1 goes up, if x increases, y increases, but at the same sort of rate. That's what we mean by proportional to each other. If they are proportional to each other, we can say they're equal to each other if there's some constant of proportionality included, which in this case is m. And playing around with this, which we've just been doing, we notice that m is all to do with the gradient of the line, and c is to do with the point at which it cuts the y-axis, called the y-intercept. So we can come up with for this particular case, a function that describes this line by finding m and c. So finally, for this particular graph, we've got y equals m, which turns out to be, what was it, 0.16, wasn't it? X plus 15.34. So this describes this line, and that's called the equation of the line. Okay, so put this in our notes. So there's the line drawn out for us with the equation of the line drawn. We can use this now. So we've got y equals 0.16 plus 15.34 to find values. So this is like a formula to find values for x or y. So if x equals 3, or if x equals 55, what's y? What would I do? Say that again. we'd write the formula and substitute in for x the value 55. So y equals 0.16 times 55 plus 15.34. Which is 24.14. And you remember for this example, x was the temperature, so that means that's a temperature of 55 degrees, and y was a volume, so that means the volume is 24.14, whatever units we're measuring the volume in. For that particular example, I think it was cubic meters. If we wanted to find x, given a value for y, we would have to rearrange this formula for y, for x, wouldn't we? So in other words, we'd have to use algebra, which we've been practicing, rearrange that formula, and we'd get a value for x. So if y equals 30 cubic meters, find x. So write down the formula. Y equals 0.16 plus 15.34. Rearrange the formula, find x.
Original volume, 24.14.
The original volume, that's the volume.
Temperature.
No, that's the volume at a temperature of 55 degrees centigrade. Yeah, so x will equal y minus 15.34 divided by 0.16, rearranging. Take 15.34 from both sides, then divide by 0.16. So for this particular case, x will equal 30 minus 15.34 over 0.16, which is it, Flavio, again?
91.625.
625.
Yeah.
Appropriate accuracy?
62.
Yeah, 91.6 is probably more like it. And that would be degrees centigrade to 3 significant figures. Agreement there? Yeah. So in other words, we've got a set of data you've all written that down? Got a set of data. From that set of data, we've found a line that fits that set of data. And the equation of that line then becomes a formula that we can use to find values for this data. So in other words, if we go back to this again, what we're saying is that at the two examples we used, when x equals 55, which is around about here somewhere, we can predict what the volume will be. For a volume of 30, which is here, we can predict what the temperature will be. Okay? And I've picked values just slightly outside this range. So what we're doing is making a big assumption. We're making the assumption that if the volume is proportional to the temperature within this range between 55 and 65, that means you get a straight line, it's going to carry on doing that. So if I draw a line on here, which is effectively what we've done, looking at this again, if I draw this line here, what I'm doing is I'm assuming that this relationship is going to carry on like this. As the temperature increases to beyond 100 degrees, 120, 130, 140 degrees, is it going to carry on like that? And equally, if the temperature falls below zero or wherever we want to go, it's going to carry on behaving like this. And that's an assumption that we must make. So within certain limits, we would say yes, okay, but obviously gases might well start to behave very differently at very low temperatures and differently at very high temperatures. So we've got to be careful the extent to which we use this formula. So as soon as we start to create formulae to describe situations from a set of data, we've got to put limits on it. We've got to make sure we don't go too far with it. And this process of using the line beyond its range is called extrapolation. We're extrapolating the data. And by that we mean we're assuming it's going to carry on behaving the way it is within the range we did our experiment in this case, and extrapolating that. If I use the formula to find a volume or a temperature within our range, which is a much safer thing to do, then I say I'm interpolating. So that's interpolation. So we come up with a formula to describe our data, which we can then use to find unknown volumes and unknown temperatures in this example. But we just have to be careful that we don't go too far outside our range, because we're making an assumption about the function if we do that. Okay. Of course, you're not likely to always have access to this software like Autograph here to allow you to do it. So what I want you to do, and what you're going to have to do for the assignment, is to actually take a set of data, draw a line of best fit on the data, and then come up with this formula. So how do we do that? Let's have a look. So finding the equation of the line from a set of data. And we'll write it as a series of steps that we can follow. So the first step, plot the data. On a graph. What sort of things do you need to consider when you plot data on a graph? Yep, set a scale. So if you're setting a scale, what sort of things do you consider?
Upper and lower limits.
Right, upper and lower limits. And so you make sure that you're going to get all your set of data on the points, making the best use of the graph paper that you've got. Orientation of the graph is entirely up to you, whether or not you use it landscape or portrait. But we tend to put the independent data, the control data, on the x-axis. So whichever way around you decide to put your graph paper, you put the independent data on the x-axis. And if you're not sure which is the independent data, that's the one that's going in nice steps, equal steps, because we're controlling it, so it's going up in 5s or 1s or 10s or something. We're controlling it, so therefore that's the independent data. The dependent data, which goes on the y-axis, generally is much more at random in the way it goes up. So we put the data on, and obviously other things like label the axes, put the units on, stuff like that. All the things you remember about plotting graphs: label the axes, units, title, etc. What is this graph supposed to be plotting? And then we draw a line of best fit. Not always is it going to be a straight line, so we would draw a freehand curve if it's suggesting a freehand curve through a set of data. Best fit means go through the middle of the points as far as you can. Okay. Yeah, good point. Who's asking the question? Sam, yeah. So if I have a set of data, that's what I was going to come to next. So if I have something like this, some points that seem to be going nicely on a straight line, but I've got one random bit of data, is that what you mean, Sam, in a way? Yeah, what would you do about this bit of data? Well, you could do, but what we could do if I had an experiment going and I was looking at the data, I would go back to check that I'd not made a mistake. It might be that whatever we're plotting here, temperature against volume, in that example, that at this particular temperature, something extraordinary happens to the gas and the volume jumps. It's more likely, though, that there's an error being made there. And so, if you're not able to go back and check your data, one spurious result like this, I would ignore it, Sam. Okay? And so your line of best fit would go through the middle of the results, apart from that one, which I would ignore. And yeah, well then that becomes a bit of a grey area then, doesn't it? You know, what you're looking for often, and by the way, just to finish this point, if you're going to ignore this, circle it and then maybe make a point that you are ignoring it and why. But yes, you're dead right. If I have another set of data and the data is more like this, it's sort of suggesting a straight line, but it's not exactly a straight line. Well then, at what point do you say, yes, it's suggesting a line of best fit and there's the line of best fit? And at what point do you say, well, actually, there is no real relationship between those two, and there's no answer to that. You know, it all depends on your experiment. Okay. Generally, though, if you've done an experiment correctly, there will be a relationship between the two. And as I said already, it's not necessarily going to be a straight line. So I might get something like this if I plot data. That certainly suggests a relationship. There is a relationship between those two, but it's not a straight line. So my line of best fit would be a curve that I'd put through the points. And then what I need to do is to recognize this. What relationship does it suggest? And that comes from experience and knowing the shapes of some curves, which we're going to come on to. Because what you then do, as I said at the beginning, is do something with this data so that you do get a straight line, and then you can carry on and find the equation of that line. Okay? So you're going to get either a curve or a straight line, and we'll certainly start off with data that suggests a straight line. I'm not going to throw you in at the deep end. Okay, so we draw our line of best fit, which is going to be initially a straight line. And then, when we've done that, number 3, we find the y-intercept. So we extend our line and find out where it cuts the y-axis. And within that lies a problem. If you plotted a graph on graph paper, and my data points look like this, and I put my line of best fit on, then the y-intercept is actually down here, or it's either at the origin. I didn't mean to actually do that. So that would mean that the y-intercept was 0, or if I just shift this to one side slightly, I have another set of data over here where the set of data, for example, looks like this, and I put my line of best fit on, it's going to cross the y-axis up here somewhere. And if I've plotted this piece of graph paper and I've made it so that this scale fits on nicely, oh dear, I've run out of room on the graph paper. And so that is a problem. So when you're setting your scale, going back to number 1, plotting the data and setting a useful scale, this idea of the useful scale, it might be worth allowing yourself room on the y-axis to extend the line up or down, so you can find the y-intercept. Okay? Because not only might the line extend upwards, which is what I was trying to do over here, if I have another set of data that looks like this, well then it looks as though the y-intercept is going to be down here, so I need to extend the line down that way to find the y-intercept down there, which is going to be negative. So it's often a good idea to just leave yourself a little bit of room on the y-axis above and below to find the y-intercept. Obviously there's no problem if you're using software, because you can just adjust the axes accordingly. So we find the y-intercept. And then, number 4, find the gradient of the line. Go to a new slide for this. Just before we leave this y-intercept, of course, the y-intercept is known as c in the equation of the line, the y-intercept c. Okay, so number 4, find the gradient of the line. M for the gradient. The letter M is used pretty well universally to represent the gradient. So here are my data points. Good smooth set of data suggesting a straight line, which I put through the middle of my data, line of best fit. I found the y-intercept, which is here, so that's C, and then I've got to find the gradient. The definition of the gradient is how far you go up the y-axis divided by how far you go along the x-axis. So to find that, we put a triangle, a right-angled triangle on the line, and it's up to you where you draw the triangle. You can start here, because that means that one of the values is 0, so that's on the x-axis, this is 0, but you don't have to. I would suggest you make the triangle nice and big, but you form a right-angled triangle on the line like that, drawing it. And where you put it is up to you. Use convenient points on the graph. That triangle doesn't have to go exactly to a data point, it can go anywhere on the graph. But you form a right-angled triangle like this, and then you measure how far up the y-axis you've gone. So this is this y direction, and that distance is from here on the y-axis, so it's this value, to here on the y-axis, which is this value. And then the distance up the y-axis is this value, subtract this value. So it's this distance from here to here will be that y distance. And similarly, on the x-axis, this is the x distance. So if you started at this point, then that makes it nice and convenient because this is 0, but you don't have to. And again, you need to go to this point and find this value, and then the x distance is from here to here. So that's your x distance, y distance. And then the gradient is just y divided by x. How far you go up divided by how far you go along. Okay, so if we put some values on, then we can see by example how this works. So for example, if this data point turned out to be 2, and this data point turned out to be 10, put some nice easy numbers on, this is 0, and let's say we come up here and we find that data point's 20. So then y is going to be from 2 to 10, which is a distance of 8. So my y direction is 8. And my x direction is from 0 to 20, so x is 20. So what's the gradient? 8 divided by 20, which is the same as 4 divided by 10, which is 0.4. So my gradient would be 0.4. Then that would mean, if I had 200 on the y and 0.1 on the x, this would be a very, very steep line, and I'd have a gradient of 200 divided by 0.1, which would be 2,000. So it just means that it would be an extremely steep slope. It's possible to do that, or am I misunderstanding you, Ben? Okay, so once we've found our y-intercept, going back to here, we've plotted our data, we've drawn our line of best fit, we found the y-intercept, we found the gradient, then we put these into the equation of the line. So the final step is to write down the equation of the line. Y equals mx plus c. And let's say for our example, y was the volume of the gas, x was the temperature of the gas, m turned out to be, in that one we've just done on the board, 0.4, and the y-intercept turned out to be 20, then I would plug those values into the equation of the line, and that would give me a formula that relates the volume and the temperature. So my final step would be, instead of y, I would write what is on the y-axis, volume, equals 0.4 times What's x represent? X represents the temperature plus 20. And that would be my formula that relates the volume and the temperature, which you could then use to find a temperature or a volume given a value. Right, let's have a look at this as an example then. Taken from the textbook on the chapter on the equation of the line, so you could find it. This is a worked problem, so the results are in the textbook, but we can have a go at it. So in an experiment demonstrating Hooke's law, are you familiar with Hooke's law? The relationship between the extension of a material and the force applied. The strain on an aluminium wire was measured for various stresses. So strain is a word that is talking about the extension, and the stress is a measure of the force on the wire. And we've got some results. Quite awkward results to put on the graph paper, which is why I picked this one. The stress, 4.9 newtons per millimeter squared, 8.7, 15, 18.4, and so on. So they're okay to plot. And we measure the strain. So the stress is going to be the thing we control. We measure the amount of force we put on the wire. So that's going to be our x-axis, our independent variable. And then on the y-axis we're going to plot the strain, the dependent variable. Stress, the strain depends on the amount of stress we apply. So we've got to plot these results. Let's have a look for a minute at how you might plot these results. Let's take this first value, 0.00007. Unit. Oh, it's no units because it's a strain. Measuring the length relating to the original length, so it's got no units. 0.407. How might we rewrite that using engineering notation? Yes, we can go 10 to the minus 3, and that would have to be 1, 2, 3, so it would be 0.07 times 10 to the minus 3, or 4, 5, 6, which is probably better in a way. So that would be 70 times 10 to the minus 6. And if we look at the last value in this table, which is 0.00039, and again make that times 10 to the minus 6, that would be equal to 390 times 10 to the minus 6. So if I have a set of data like this to plot on a piece of graph paper, what I would do is I'd form my results table. I'd put my x, which is my stress, down. So 4.9, 8.7, and so on. So I'd suggest you do that. But my strain axis, I'm going to write my strain times 10 to the minus 6. And if I put that in there, that means all my following results are times 10 to the minus 6. So then what I plot is, the first one is 70. The second one will be, if I move this 1, 2, 3, 4, 5, 6 places to the right, that will be 130. And so on. And so then when I come to plot the graph, they look more reasonable results to put on the graph paper. I'm not trying to write my scale 0.0001, 0.0002, and so on. I'm using numbers that are easy to put on the graph paper. That's a good tip, okay? Use engineering notation to allow you to put more straightforward numbers on the graph paper rather than trying to plot very large or very small numbers. Okay? So I'd like to have a go at this question. I'll leave it up on the board, so if you've not got your graph paper here, you can write down the values, but I suggest you make yourself up a results table like this, and then you can plot the graph. I'll bring round some graph paper, and then you can go through these steps. Plot the graph, put on the line of best fit, find the y-intercept and the gradient.